Okay, so hi everybody. I think it is 10 now, and we are going to start our session for the program comprehension. This is like a 2 demo session, and we have 4 2 demos, and our each like presentation will be 15 minutes, and our first presenter will be Hongzhou Fang from Drexel University on CIDR concept-based interactive design recovery.
Hello. Okay. Hello. I'm going to present our two CIDR, or concept-based interactive design recovery. I'm Hongzhou Fang, a PhD student from Drexel University. And other co-authors of these tools are Professor Yuanfang Cai, Professor Rick Kussman, and another PhD student, Jason Lefevre. There are many existing tools and methods which help developers to understand the software system. Many tools visualize package structures or dependency graph of the system. And also, architecture recovery and feature location are two well-researched fields related to this topic. The existing architecture recovery methods generate the file clusters based on some specific rationales, while they usually do not provide the following guidance which can be useful to the developers. First, they do not reveal the concepts of each calculated clusters, and they do not provide insight about the design quality, such as if the design is good or bad, or if the design contains any architecture issues. They also do not recover a portion of the design that is strongly related to a maintenance task, such as implementing a new feature or fixing a bug in an existing feature. To help answer these questions, we create our tool, CIDR. Like other tools, it recovers and visualizes a high-level design of a given system. It combines multiple clustering algorithms to generate a simple and straightforward graph. Each cluster in the graph is labeled with representative concepts using information retrieval methods. Our tool also detect and highlight design problems or architecture issues, such as clique or a group of highly coupled files. To provide a fine granularity view of the system, our tool extracts function groups defined as a set of files used by one single functionality or feature, and also cross-cutting concepts or concerns that appear in multiple function groups. Finally, our tool provides an interactive partial design recovery using user-specified concepts based on the need of the maintenance tasks. This graph shows all the major components of our approach, which contains source code processing, function clustering, concept labeling, and interactive recovery. In the source code processing component, we use two third-party tools, Depends and Deviate, which process the source code into dependency and generate design rule hierarchy clustering files for the later components. In the function clustering component, we cluster the output of the previous component into function group clusters, and then we apply multiple clustering algorithms to generate uses hierarchy graph, which is a high-level graph, shows how functions uses each other. In this component, we also detect architecture issues. We currently just implement clique detection. In the concept labeling component, all the keyword concepts are extracted from files inside each clusters, and each clusters will be labeled with the concepts using TF-IDF ranking. We call the result graph a concept hierarchy graph. In the last component, interactive the interactive recovery components enables user to discover the high-level design of the system using the concept hierarchy view, or a portion of the design using the facade hierarchy view. Now I'm going to show a live demo of our tool. Let me switch the screen share. Oh, it's not showing correctly. Okay, we are using depends, a multi-language dependency extraction tool as our example. Can you all see the screen? Okay. So the concept hierarchy view shows the high-level design of the system. Each node is a concept cluster, contains multiple function groups, and each arrow indicates a use relation between two clusters. Each node is naming with the top ranking concepts, and it also shows the click inside each cluster. To keep the overall graph simple, the cider by default shrink the graph to a height of 4. And we can use the buttons, the plus and the minus button, to expand or collapse the overall graph. On the left side of the window, there is a table show all the click inside the system. If we select one single node, all the incoming and outgoing relation will be highlighted, and the details will be shown on the left side, which including a short description, all top concepts in the cluster, and all the function groups in the cluster. We can also dive into one specific click. All the files in the click and the relations among these files will be shown in this click view. In the function group tab, we can explore all the cross-cutting concepts. There are two tables, a keyword concept table and a function group clusters table. We can filter out the function groups by selecting one or more concepts in the keyword table. For example, the dependency is a cross-cutting concept in the depends. And if we select dependency, we can see there are 78 function groups contain the keyword dependency. And by selecting multiple function groups, we can see a similarity relation between these function groups. As we can see, function group number 6 is a subset of function group number 2. In the facade hierarchy view, there is a table of concepts with all related function groups to one concept. For example, if we are going to implement a new language support for depends, we can use C++ in existing language support as a reference. If we select C++, all the function groups related to C++ will show in the table, and their relation will be shown as a graph. The function groups contain the concept C++ are highlighted in green, and other function groups using these green clusters will be shown in blue. And we can see Ruby processor is using function group contains C++. If we are interested in such relationship, we can also select Ruby. And now we can see Ruby import lookup strategy is using C++ import lookup strategy, which is confirmed by the depends developer that is a forgotten dependency shortcut, which should not exist. We also have a download tab, which allows user to download extra resource related to the project. So if we still have time, we can go back to the slides. To evaluate our tool, we conducted an explorative case studies among 2 open source projects, FEMA and Depends. We focus on three different aspects of our tool. If our tool does our tool help with design structure comprehension? And the result is that FEMA about our tool in their new developer onboarding process, which proves our tool is helpful to new developers to understand their system. And if our tool provides design quality insights, which the result is that the Depends designer were able to identify the techno depths, which is that 32 file click we showed earlier, and the undesired dependency. And the final aspect is that if our tool supports the maintenance task, and the survey of the evaluation shows that most developers agree that Cider is useful to support the maintenance task and leaves positive comments. In the future, we are going to implement or integrate more architecture issue detection. We are also going to explore more effective information retrieval methods other than TF-IDF rankings. We are also going to improve the usability of our interface and conduct a larger scale evaluation. That's everything I have today for Cider. Our tool recover and visualize a high-level design of the system, detect and highlight design problems, extract function groups and cross-cutting concepts. And also it provides an interactive partial design recovery based on user-specified concepts. Any questions?
Any questions from the audience? Thanks for the presentation.
I do have a question if there's time.
Yes.
Yeah. So I did spend some time thinking about concepts and just representing concepts, and I was wondering how you did that for Cider. So, in a sense, what exactly constitutes a concept for Cider? Is it just any term that may happen, or do you have a way to maybe aggregate synonyms? See that some words might be a concept and other words might not be a concept.
Yeah, currently we are using all the keyword extract from file names using as concepts, but we are also trying using different models to find which words are more important to others, which can be more appropriate, can be more important concepts, instead of using all the words from file names.
So I guess, and do you have any way to maybe merge small variations, like if a word appears in the plural form versus singular, ideally that would be the same concept. Did you consider that?
Yes, so for now we are using TF-IDF since it's the most straightforward way to get the high frequency keywords as the top level concepts. But I think there's other way we can utilize the dependency information to conduct better results other than just using the frequency information.
Okay, thank you very much.
We also have some questions in the chat box. I think we are already 15. So I think, Hongzhou, you can answer the questions in the chat box so that everybody can see it.
Sure, no problem. Thank you very much.
Okay, thanks. Thanks, Hongzhou. Our second presentation will be from Yao. It's on Nature CC, an open source toolkit for code intelligence. So Yao, maybe you want to share the screen?
So could you see my screen now?
I can see it.
Hello, everyone. My name is Yao Wan from the Huadong University of Science and Technology, China. Where I will present our demo paper, Nature CC, an open source toolkit for code intelligence. This work is joint with some professors and researchers from the University of Technology, Sydney, University of Illinois at Chicago, University of Newcastle, and Google Research and Salesforce Research. So, firstly, what is the code intelligence? In my view, code intelligence is about applying machine learning techniques, especially including the deep learning techniques, to analyze the big corpus of source code, which are collected from open source platforms such as the GitHub and the Stack Overflow. And the code intelligence hot research topic in the software engineering community. And there have been many related tasks such as the code summarization, code retrieval, and the code completion. And recently, we have witnessed several popular tools which have been developed by bigger companies such as the OpenAI Copilot and the transcoder, which is from the Facebook. Also, despite much progress have been made in code intelligence, from our investigation, we think that there have been two major limitations. The first limitation is that in our current community, there is lack of standard algorithm implementation and a toolkit for reproducing the results of existing models. So we can say in many papers, the authors will develop their they will implement their own approach using GitHub repos, but there is no standard toolkits to reproduce these results. And the second limitation is that we are lacking of benchmarks for fair comparison between different models. And in many software engineering papers, the authors will claim that their models can outperform other baseline models. So, but it is hard to determine whether their performance gain is from their design model or from other deep learning training tricks. So, I think it is very important to build a benchmark for this kind of code intelligence tasks. However, we can say in the natural language processing community, actually there have been many open source toolkits such as the fail sequence from the Facebook and the Allen NLP and the Stanza, many open source toolkits. So it motivates us to design a similar toolkit for the source code. We think that it will be beneficial to our software engineering community. So in our work, we developed the open source toolkit termed the Nature CC. The Nature CC can be seen as the which is the short for the natural code comprehension. So this slide summarizes some features of our natural CC. Firstly, in our toolkit, we have connected a collection of code corpus with different processing scripts, which contains many compiler scripts. Secondly, we also present an extensible framework, which is built on a registry mechanism, and so our toolkit only need to implement models by intentionally one of our templates and register them. Certainly, we also perform a benchmark for several popular code intelligence related tasks, such as code retrieval, code summation, and code computation. This is the framework of our natural CC. In our toolkit, we built 4 major folders. The first one is the data set, which is used for data processing. The natural CC folder is our core module, which consists of the data folder, the tasks folder, the models folder, and several modules, several deep learning modules, and several deep learning optimizers and trainers. The third one is the third-party folder, which is used to include several open source package, such as some open project for evaluation, and we also developed a GUI in graph user interface in the GUI folder. Okay, this is the pipeline of our natural CC. Given a corpus of code snippets, we first tokenize the code snippets and build a vocabulary. Then we use some compiler tools to extract some features such as the AST, the control flow graph, and the LLVMIR. Then we feed the features to a data node module. Then the data module will generate a series of batches, which can be used to our deep learning models. In our deep we first perform the code comprehension. Currently, we have included several popular code representation modules such as the RNN and the GNN and transformer and pre-training models such as BERT. In our tasks models, we have implemented several downstream tasks such as code computation, code documentation, code retrieval, and type inference. And in our evaluation process, we have integrated several popular evaluation metrics such as the blue RAJ for the summarization tasks and several the MRR MAP for retrieval tasks and so on. Okay, this is the pipeline of natural CC. Then we also perform several benchmarks on 3 different downstream tasks, such as the code summarization, code retrieval, and code computation. This figure summarizes the experiment results using our toolkit. When compared with the results published in the original papers, we can see our toolkit can achieve similar results. And we also show how to use our toolkit. Firstly, if we want to build a new task, name the competition task, we can create a completion task class in the corresponding completion.py. And this class is alone with a decorator register task around. Then we can build a recurrent neural network model for code competition. Here we define a new class sequence RNN model in the sequence RNN.py, which is inherits the NCC language model. After building a model, then we can train our model using the following pipelines. Firstly, we can set up the task, and then we build our model and the criterion, and then we build the trainer, and the trainer will iteratively training our model. Okay, then if I have time, I will try to show a level demonstration of our toolkit. Okay, actually, we have built a web page for our project Nature CC. In this web page, we have a demo tab. When clicking this demo tab, we can move to our demonstration. Actually, in our web page, we can try several code intelligence tasks we have implemented. For example, for the code summarization task, we have implemented several popular models, such as the transformer or the sequence-to-sequence model. For example, if we we choose the transformer model and we select a case of code snippet. This is the ground truth of our text summary. Okay, if we click the run button, then our model will inference the results. Okay, this is the return results, which is a natural language summary generated by our implemented transformer model. Okay, then for the code retrieval task, we also implemented several popular models, such as the bidirectional recurrent neural network and the convolutional neural network and the embryo and self-attention based models. For example, if we choose the bidirectional recurrent neural network, and this is our input natural language query. If we click the run button, and then we can retrieve several relevant code snippets. Okay, note that since our code is running on 2 GPU cores, so maybe it is slow for this process. Okay, I think maybe it's a little bit too slow. Okay, so I think I will move forward. And this is our demo for Nature CC. And here we also built this is the open source and our open source toolkit in GitHub. If you are interested, you can visit our GitHub page and find some related sources. Okay. Okay, this is a retrieval the code snippet. Okay, then I will go back to the slides. Okay, this is the GitHub repository of our Nature CC toolkit, and this is the web page. This is the URL, and our team is named CodeMind. This is our name, the name of our team. Okay, thanks for your attention. Any questions? And I will stop the sharing my screen. Hello, Professor Wang. I think you have muted.
Oh, I'm sorry. Yeah. I'm sorry. Yeah. I think, then we, because the time is limited, so we're going to ask all the audience if you have any questions to put in the chat box, and you can answer the question in the chat box, and so that everybody can see it.
Okay, sure.
So our next presentation is from, so who is going to, I think we have all the authors coming. I think from Nakshatar and Ashutosh on cost packs, a program comprehension tool for novice programmers.
Yes, I'll be presenting.
Okay.
Yeah. Let me quickly share my screen. Let me know once the screen is visible.
I can see it.
Okay. So, hello everyone. In this talk, we'll be having a look at COSPEX, a program comprehension tool for novice programmers. This tool was developed by Nakshatra Gupta, myself, Ashutosh Rajput, and Professor Sridhar Chimlakonda of Risha Lab at IIT Tirupati, India. So the agenda of this talk is to cover the problem overview of program comprehension, the concept map associated with it, the objectives for developing the tool, the implementation of our tool, the evaluation methodology and results related to cost specs, and the strength, weakness, and opportunities analysis. So as we all know, program comprehension is one of the key activities in software development lifecycle. Developers often come across unfamiliar code during software maintenance. The comprehension of such unfamiliar code is a tedious, time-consuming, and a complex activity. Therefore, the developers often depend on the existing software documentation to get the meaning of the program. However, this documentation is often outdated and incomplete since the programmers do not update it constantly with all the code changes. Therefore, an automated tool that can generate summaries for programs and present them in an effective way is an effective approach for program comprehension. So, extracting information from source code can be done in two ways. One is static source code analysis, another is dynamic source code analysis. So the existing approaches which leverage static source code analysis, they often depend on information retrieval from source code or neural networks, which generate natural language descriptions by predicting the next words in the sequence for the summaries. There have been some approaches which have leveraged both information retrieval and neural network based approaches to generate the summaries. So in static source code analysis, generally the source code is treated as a text file, and we extract the important keywords from the source code. In this case, the relationships between different key components of the code are not considered, and hence the summaries miss out on the semantics involved in the program. On the other hand, we have dynamic source code analysis. It involves executing the code snippet and extracting key information during runtime. There is a major assumption in this kind of analysis. It is that the source code snippet which we are extracting the information from has to be executable, and the execution time of the source code has to be reasonably less. The existing approaches majorly capture the higher level abstract information of the source code and do not delve into the lower level execution insights into the program. Therefore, from our end, we propose COSPEX, comprehension using summarization via program execution. It is a tool that leverages dynamic analysis to extract key information during program execution and presents it in an interactive form so that the programs can comprehend the meaning of the program. The tool also presents lower level information along with data flow inside the program. Moving on, the objectives involved in creating this tool were to create an easy to use program comprehension tool, especially for novice programmers, which uses dynamic analysis techniques. We also wanted to aid the programmers in quicker understanding of unfamiliar projects and thus ease the process of comprehending the code snippets. We also aim to provide insights into the real-time execution of a program and provide a complete overview of executed lines of code along with the history of all the variable value changes. Coming to the implementation, COSPEX involves taking the code snippet and test cases from the programmers. It then attaches a hook to the test code snippet and cases, which then interprets the program runtime and takes out the important information available in the stack frame, in the line call events, in the function call events, and then it compiles our information instances, which we then summarize in the form of dynamic summaries. Coming to the evaluation methodology, we performed a preliminary user story with 14 undergraduate students studying in their second to fourth semester in computer science and engineering department. So the students here were provided with 6 code snippets with varying complexity and their corresponding outputs generated by our tool. And then the participants were navigated to a survey where they were asked certain questions which interpreted their understanding of the program and also tested the feasibility and effectiveness of our tool. The questions were split into 2 parts. The first 6 questions were answerable on a scale of 1 to 5. And the next 2 questions were short descriptive questions where we asked the participants their review and the areas of improvement in the tool as according to them. Coming to the results, we received pretty good results for our tool from all the participants. So all the first 6 questions were responded with everyone agreeing that the tool helps them understand the program in a better way, and it is feasible for understanding the program in a day-to-day life. The last 2 questions, we received the responses such as the approach summarizes the working step by step and gives a better understanding of the source code. It explains the code in a step-by-step debugging manner. The approach also helps us to understand the complete flow of the program. So from these responses, we can interpret that the tool was successful in novice programming environment to provide insights into the runtime of the program and thus helping in comprehension of the program. Now coming to the SW analysis of the tool. COSPEX is one of the initial tools aimed at analyzing Python code snippets dynamically to aid the program comprehension process. It also leverages dynamic analysis. Therefore, it can extract the key relationships between code components during its runtime. It can also present the data flow of the complete program execution and thus providing an overview of the program. Finally, these summaries are presented in a user-friendly interface so that the program can be better explained to novice programmers through an interactive form. There are also some weaknesses associated with dynamic analysis of source code. Firstly, the tool does not have an automated test case generation part. The programmer has to manually input the test cases along with the code snippet. Also, if the program consists of different branches, such as if and else branch, only the executed parts of the program for that test case will be analyzed. Currently, we have compiled our summary through hard-coded natural language phrases. And also, if the program consists of nested loops, extremely large number of nested loops, the UI can sometimes get muddled. There are various opportunities in the future where COSPEX can be improved. Firstly, we can add an automated test case generation part to the tool. We can also leverage natural language processing techniques to generate the summaries from our dynamic information instances. Also, the patterns in variable change during the runtime can be identified and presented in a more effective way. So to conclude, we developed a tool that dynamically analyzed source code files and presented the extracted information in an interactive form for program comprehension. The tool included interactive interfaces for different code components, which helped in better program understanding. And also we evaluated our tool through user story and observed that the tool proved to be useful in explaining the working of a program, especially in a novice programming environment. In future, we plan to automate the process of test case generation. This will make the process less effort intensive for the developers and also cover all the branches of the code for better comprehension. We also plan to leverage static analysis, that is NLP approaches, along with dynamic analysis to improve the readability of our summaries so that the participants can understand the program in a much better way. So that is it from my end. Now I'd like to request Nakshatru to present the demo of the tool. Thank you.
Hello everyone. Is my screen visible? Okay. So this is the demo for Cospex. So this has been developed as a plugin for Atom IDE. So to generate a worked out example, the user has to provide the input code snippet as well as some test cases. Here the user has provided 2 test cases. So to generate the worked out example, simply press Ctrl+Alt+Q. And a pop-up will open, which contains the summary of uh, the input code test code snippet. Now, as you can see in this, at the top, you can see the name of the file, followed by 2 boxes. Each collapsible box represents a function call. And as the user has provided 2 code snippets, 2 test cases, therefore the quick sort function has been called twice. So in the first collapsible box, you can see in the top half, quick sort function has been called with argument this. And below that, you can see the quick sort function has returned the sorted arrangement of the array. And finally, you can see the output of the program. So to know more about the quick sort function, you can simply click on it to expand. In this, step-by-step execution details will be presented to you. So at the top, here you can see the blue lines are the lines of code preceded by the line number. And below them in black font, you can see a simple explanation of what that line of code did. So here you can see as a collection has been passed in as argument to quicksort function, therefore collection has been introduced with this value. And further, if length of collection is less than 2, it has been evaluated as false, as the length of collection is greater than 2. In the next line, pivot is equal to collection.pop. You can see a collection, the value of collection has changed from this to this, and pivot is equal to 5 has been introduced. Moreover, you can hover over some functions to see a description of what that particular function does. And you can hover over variables to see the history of how the value of that variable has changed. Further, you can see the next 2 lines are pretty simple. They need no explanation. After that, in this green box, this is a loop. All the loops are represented in this slideshow manner. So the user can move through the iterations left or right to see which particular iteration they want to understand. So if you move a few iterations ahead, hovering over greater will show you a history of how the value of greater has changed. And finally, in the return, quick sort function has been called again twice. So two more collapsible boxes have been generated, in which we can see, based on the argument passed, how they have functioned. So if the user want to see more execution details about this quick sort, they can simply expand it to again see the information, and the user can determine the granularity with which they want to see the execution details. Similarly, it has been repeated for the next test case. So yeah, that is it for the demo. Thank you.
Okay. Nice presentation in demo. So it seems that we are also like running a little bit out of time, but I think we can take one live question if anyone wants to ask. or we just we already have a lot of questions I see in the chat box. So I think you have a lot to do, Jeffrey and the other author. Yeah, you want to answer the questions. I think we at least have 3 questions there. Okay.
Definitely.
Yeah. So then we're going to go to our last demo. Our last demo is, I think, Rafi, you are going to present it, right? A tool for rejuvenating feature logging levels via Git histories and degree of interest.
Great. Yeah, thank you. Sorry, I have a little bit of problem here with my browser. Looks like it only shares tabs. Let me just open up my PDF in the browser here. Sorry about that.
Fine. Yeah.
All right, 1 second. Sorry about that. Okay. Yeah. All right, I think I can, let me try it now. Let's get my tab working. All right. All right, can everyone see my PDF? Okay.
Yeah, I can see it now.
All right, great. Yeah, it's not ideal,
Great.
but so yeah, my name is Rafi Kachadorian. I am from City University of New York, Hunter College. This is joint work with Yiming Tang at Concordia University, Alan Spector, also at Hunter College, and Mehdi Ben-Khurzadeh from Oakland University. And I will be presenting a tool for rejuvenating feature logging statement levels via Git histories and degree of interest. So logging is pervasive in modern software. Big data systems in particular deal with a lot of data, a lot of transactions. And typically, source code is tangled and scattered with logging statements capturing important events that occur during the execution of software systems. And the logging statements are essential for reporting various events that happen during the execution, including perhaps security or privacy breaches. So modern software is very heavy in features these days, implementing hundreds of, or if not thousands of features. And logging statements, although more informational in this context, also capture important aspects of the particular feature implementations that they surround. And they're useful for validating the feature implementations, particularly regarding like diagnosing any issues or unintended interactions with other features. However, too much logging can cause information overload. Moreover, if there's a problem, it makes post-mortem analysis difficult to diagnose. The logs get very heavy, and the log files get very, very large. And understanding system behavior in production and diagnosing production issues and deployment issues can be a challenge. Also challenging during development, as logs pertaining to auxiliary features are tangled or secondary features or cross-cutting concerns are tangled with those that are of the core functionality. So this is actually not a post-mortem, but actually like during development and usually using logging statements during debugging sessions, for example. So we call those kinds of logging statements feature logging statements. And logging statements in general are typically associated with a log level. And what the level does is dictates whether the log should be emitted at all or how it should be emitted. Sometimes there's log post processors that will send like certain colors to particular log levels, for example, like critical or would be red, for example, or there could be other kind of post processing being done on the levels themselves. Here we have an example logging statement that outputs the system health if and only if the runtime log level of the logging object here, logger, is less than or equal to finer. And this would be configured on the logger object ahead of time, either through a configuration file or programmatically through a method call or an instance method call. As software evolves, logging statements levels correlated with the surrounding feature implementations may also need to be changed as well, particularly regarding the levels. And developers often fail to initially set the appropriate log levels, and unfortunately, sometime afterward, they have to change them to fit the context. So our supposition is that ideally feature logging levels would evolve with the system code that they annotate or they document, I should say, as that code is being developed. And what I mean by that is that higher log levels, so for example, level info would be a little bit higher than fine or finer, would be assigned to logs corresponding to features with more current stakeholder interest at the time. And you would have lower log levels for those that are less interesting to the developer as they're developing the feature. So for example, finest, which may be a level that's not admitted at all. So the ideal situation that we see is that you would have the feature logging levels that pertain to the feature you're currently developing appear in your logs during perhaps debugging sessions, and ones that are like maybe for auxiliary features or other core features that are not under active development would be sent to the foreground by using lower logging levels, for example, fine, finer, or finest. So we set out to automate this approach. It's called log level rejuvenation. This is our kind of overall architecture, and there's more details in the paper. I'll just kind of briefly go over the top level concepts. So we automatically evolve feature logging statement levels. And we do this by mining Git repositories, the history of the code edits made in the project. And we do that to discover the quote unquote interestingness of the code surrounding particular feature logging statements. And we look to find mismatches between the interesting level of the surrounding code and the level of the logging statements. To do this, we adapt a degree of interest model, or DOI for short, from the Mylan Eclipse plugin, which keeps track of particular elements in the IDE. Depending on how interesting they are, it will bring those to the forefront and push other ones to the background. And you can correlate the DOI models with like issues, for example, like in GitHub or maybe in Jira, and you can do context switching. And what we did here is we actually made a unified model that's based on Git histories. So the model actually is not traditionally the model is manipulated by like mouse clicks or edits to a file. Here we actually modified the algorithm to bump up the model depending on the number of edits made to particular files in the Git history, and vice versa. So here's a little screenshot of our plugin. It's an Eclipse plugin. It currently works on Java, and it supports a number of different frameworks for logging that Java has. And it's implemented as an open source plugin to the Eclipse IDE. If you don't use Eclipse, it also can be used in popular build systems via like Maven plugins, for example. Like I said, it supports 2 frameworks right now, Self4J and Java util logging, which is a built-in Java logging framework, JUL for short. The implementation integrates both JGit and Mylan, and here is a URL where you can download the plugin. Okay, so I'd like to do a tool demonstration now. Although, let's see, I'm not sure if I can do that within my browser, unfortunately. So sorry, this is my first tool demonstration on this platform. Let me see if I can do my window. Okay, I can. All right, very good. So let me share my Eclipse workspace here. I'm just going to make sure that's appearing on the screen. All right, great. So I have a kind of small example set up here from our full journal paper, but this actually does work better when you have a larger example, just because it's a statistical model. So here we have a Wombat class that has a logger attached to it here as a field, and wombats have a temperature. Let's say, their body temperature. There's also an instance field here that records the previous temperature taken. And there is here a public method setter for the temperature that records the current temperature and then sets the new temperature to the incoming argument. it documents this feature using the logger. So it sets, it outputs the temperature that's being set and also outputs the old temperature. These are both in the finer level currently. There's also a main function, which instantiates the wombat. It also gets the temperature from standard input here and sets it on the wombat W. Then it tries to write to a file. It writes to an output file, output.txt, the wombat itself. And if there is an error writing to the file, we have a severe logging statement here that says we cannot open the file, and then we throw the exception. So this does work on Git history. So I did set up a few different versions. This is the first version. So let me open up the second version. So there are going to be a number of edits to here, and we're going to see how the logging levels change as a result of the edits to the files. So let me just swap this a little bit here. So I'm going to expand this. So what we're going to do first is actually we're going to implement a feature here where we check for non-negative temperatures. So we're only going to accept non-negative temperatures. So if the temperature is greater than 0, then we perform what we did before. Otherwise, we're going to throw a legal argument exception. Also, we're going to, instead of throw an exception immediately after receiving an invalid temperature, we're going to ask the user for a new one. So if we do get an illegal argument exception when we call the set temperature, right, we're going to ask the user to enter a new temperature and to try again, and that goes on until the temperature is set correctly. Okay, so some time goes on. There's now version 3. So there's another change made to the wombat class here. And we have also another feature here being added. Let me switch this over so the right side has the new code. Okay, so we add another feature here where we issue a warning if the temperature has arisen above 5%. And that's version 3. So we have 3 different versions, right? A few different features being implemented. And let's see how we can modify the log levels using our tool to reflect the kind of current stakeholder interest in these particular features. So the way this works is you click on the, I'm going to go a little bit fast here, on the project here. I know I'm running out of time, apologize. And then you activate the curl Myelin task. It works with Git histories, and we have a feature working for the Myelin tasks already. I'll turn this off. So that's one thing you have to do at the moment. And then we select the project here, and I'm going to pick rejuvenate my log levels. There's a couple of different options here. I'm just going to go straight through. I was going to go a few iterations here, but that's okay. We'll just go through one of them. So we're going to select this option to treat logging, severe, and config. This is with JUL, Java Utility Logging, as non-traditional log levels. They're actually going to be categories, so we're not going to modify those. We're going to use the Git history to rejuvenate the log levels. We're also going to click here not to decrease the levels in catch blocks in case there are errors. In the future, we'd like to automate some of these options. And there's also a transformation distance maximum. I'll set that to 1 so we don't have like super drastic changes. And lastly, there's a end value here, which is like a maximum number of Git commits to traverse. There's not too many in this one, so we'll just leave it at 100. Okay, so the result is as follows. So since there was more interest here, let me swap this again. So I have the original on the left here. So this is our original code. I modified a little bit. I added a few more versions here just to get the decay working. So things will get lower. Decay, it's a little bit more slow than increasing. So here we went from finer to fine because there's more interest levels, and the surrounding code is more quote unquote interesting or being edited more often than some of the other code. So this one increases the fine. And then finally down here, this feature didn't have many edits to it as recently as the other one. So that one decreases, so it goes from finer to finest. Also to note that we didn't touch some of the other ones. For example, one in this catch block, there's some others like that we would not want to touch because they're more not informational, but rather like warnings or severe errors. Okay, so in the paper, there's some evaluation plans. I'm sorry, I didn't have time to get to that. And for future work, like I said, we'd like to incorporate the myelin model as well, and also automate some of the options, perhaps using like AI or something like that. So machine learning. Thank you.